Hello everybody, I'm Daniel, and today I'm going to present to you our research paper, Osiris Automated Discovery of Microarchitectural Side Channels. Our research focuses to support CPU vendors and researchers in finding side channels in modern CPUs. But before we dive deeper into that, let's take a look at where we started our project in the first place. So from today's point of view, we know for many years that side channel attacks or microarchitectural side channel attacks pose a severe threat on modern systems. For example, you can use such side channels such as flush and reload or prime and probe, for example, to attack otherwise secure implementations of cryptographic protocols such as RSA or AES. And not only that, but since 2018 we know about transient-execution attacks such as Spectre or Meltdown, and they also require on side channels to work. But the problem that still arises is that most side channels we know by today are the result of a very time-consuming and labor-intensive process, as researchers often spend days or even weeks reading through patents and manuals to eventually come up with the idea of one such side channel. And our research now supports the goal of automating this research by fuzzing for such side channels. And the idea is that instead of fuzzing some software application, we fuzz the underlying CPU hardware directly. But to understand how we can do so, we first need to understand how such a side channel actually looks like. And for this, here on the slide, you can see the side channel flush and reload, which encodes information inside the CPU cache and later on decodes it again. And to do so, flush and reload first removes some memory address from the CPU cache so that it's no longer cached, and accessing it is quite slow. And then afterwards, eventually we access our memory address again. And for now, let's say if we want to encode a 0-bit, we do not access it. But if we want to encode a 1-bit, we access it again. And in our third sequence, we then time an access to this memory address. And what we observe now looks basically like the following. So if the first access in our second sequence was not there, then we observe a cache miss, as our memory was previously flushed. So our timing is up to 200 cycles. But if this access is actually happened, because we wanted to encode a 1, then we see that our access is much faster and we can actually distinguish that with a very precise timer. And by that, we can decode and encode our information inside the CPU cache. If you now take a look at similar such side channels, you start seeing some similarities between them. And more precisely, we defer to them as consisting of 3 different sequences. Our first sequence is the so-called reset sequence, as we reset our CPU component to a known state. In this case, the state is our memory address is no longer in the CPU cache. In our second sequence then, we eventually trigger a change in this state. So in this case, if our trigger sequence is executed, we trigger the state change to the memory address is now in the cache. And our third sequence then times some memory addresses, or for example, other instructions. And based on this timing, we observe whether or not the trigger sequence was previously executed. And if you visualize this a little bit different, you see the very interesting part about this is that we can abstract away from all these details of, for example, the CPU cache. We can just say that our microarchitectural CPU component is just consisting of 2 different states, namely S0 and S1 for encoding a 0-bit or encoding a 1-bit. And now our reset sequence just brings us back to our state S0, and our trigger sequence brings us back to our state S1. And the very nice thing there is that if our measurement sequence can actually tell us whether or not we're currently in state S1 or S0, we can encode 1 bit of information. Not only that, but given 3 arbitrary sequences, we can actually test whether they form such a side channel or not. And to do so, we just execute the reset sequence first, followed by the measurement sequence. So this then basically gives us the timing of our state S0, or what you can also call it like our cold path. Then in our second case, we execute the reset sequence again, but this time we follow it by the trigger sequence. So now we have the timing of our state S1, or our hot path. And if those 2 timings are actually distinguishable, we can report them as a working side channel. And to give you an example of that, let's assume all these sequences consist of the x86 instruction increment of a memory address, which accesses a memory address and increments its value by 1. So now in our first case, we first access a memory address and later on access it again in our measurement. And this is a cache hit, so this is very fast. For our second case, things are very similar here. We once again have a cache hit there, and it's still very fast. So this is not a timing side channel, as we cannot distinguish those two timings. But if we change our example slightly, so for example, we use the clflush instruction, which removes an address from the CPU cache as a reset instruction, then things are different. So in the first case, we first remove our memory from the CPU cache and access it. So this gives us a cache miss, which is very slow. But in the other case, if our trigger was previously executed, then this trigger sequence brings our memory back to the CPU cache, and we observe a cache hit. So this is very fast. And in this case now, we can distinguish those two timings, and we have a working side channel. And with this idea in our mind, we can build our fuzzer Osiris, which fuzzes x86 CPUs for their potentially unknown side channels. And the idea is very similar, it's very easy. So we start by an human-readable and machine-readable x86 instruction set. For example, the XML description of the x86 set. And then we just generate sequence triples out of them. And for that, we assume that every such sequence consists of exactly one x86 instruction. And then we just generate all possible permutations. And in our second stage, we just execute them all. And we execute them basically like you've seen on the previous slide. And we just keep them, keep those triples that actually report a working side channel. In our third stage, we just confirm these results again by randomizing the order of execution and adjusting our thresholds a little bit to just remove false positives during our measurements. In our fourth stage, we then cluster our results. For example, for flush and reload, you will end up with thousands of different sequence triples that all form the side channel flush and reload. So we just cluster them to make our result more manageable. And then in the end, we end up with our report that researchers can manually investigate further. And we actually tested our tool on 5 different CPUs consisting of AMD and Intel CPUs. And the first thing that we observed was that our runtime was up to 4 days per system, or more precisely per CPU. And the amount or the number of clusters that we observed per CPU was less than 30. So we think it's quite fair to say that less than 30 clusters is a number that you can manually investigate further. And the very interesting question now is, what did we found when taking a look at these clusters? And it turns out that we found different novel side channels, and we also found some known side channels. So for the known side channels, we, for example, found flush and reload. But for our novel side channels, we also, for example, found the ADI-RAND-based side channel. So a previously unknown side channel working with the ADI-RAND instruction of x86, which uses the random number generator of x86 CPUs. Here on the right-hand side of the slide, you can actually see the timing difference of this side channel. So we wanted to go one step ahead here, wanted to make sure that our side channels are actually having some practical impact. So for that, we evaluated them in 3 different case studies. In our first case study, we took a look at our ADI-RAND side channel and we built a covert channel out of it. So we had a sender and a receiver process, and we were able to transmit information between them. And not only across cores, but also across virtual machines in the AWS cloud. And if you now compare our side channel to similar side channels or similar covert channels, you'll see that we do not need shared memory or shared CPU cache. And hence, it's also very hard to detect our covert channel because we do not leave any important traces in the CPU cache. And there are also, to the best of our knowledge, no related performance counters that you could use to detect this covert channel. In our second case study, we then took a look at transient execution attacks. And more precisely, we mounted Spectre and Meltdown proof-of-concept implementations using our novel side channels. Our Spectre proof-of-concept was then roughly 2.4 times as fast as a similar non-cache-based side channel, namely the ABX2 side channel used in the NetSpectre paper. And our Meltdown proof-of-concept, using one of our side channels we named Stream+Reload, was actually able to leak almost 8 bytes at once whereas previous work was only able to leak up to 3 bytes at once. So we think it's fair to say that our side channels can be used to improve the performance of actually known or yet known transient execution attacks. And in our third case study, we took a manual look at one of the instructions reported by Osiris, namely the move with non-temporal hints. And based on our experiments with this instruction, we came up with a KASLR break, which is based on transient execution. And the interesting part about our KASLR break is that it actually works on new Intel CPUs like the Ice Lake and Comet Lake, where many other KASLR breaks stopped working. And as I'm already now running out of time, let's summarize our paper for today. So our work denotes side channels as sequence triples. And then, based on this notion of sequence triples, we develop our fuzzer or Cywitz, which fuzzes for such timing side channels in modern CPUs. With Osiris, we then discovered 4 novel side channels, which we further evaluated in 3 different case studies. And as we believe that open research is a very important part for our community, we open sourced our fuzzer on GitHub so that you can play around with it. And by that, I'm at the end of today's talk, and I thank you all for your attention. I hope I've spiked some interest in our research, and feel free to check out our paper or also our tool on GitHub and eventually find some new side channels in your own CPUs. Thanks. Bye.